So, as I mentioned yesterday, solving quadratics wasn't actually the reason the complex numbers evolved. However, they certainly are extremely useful in solving quadratics. So something like this. X squared plus 3x plus 7 obviously doesn't factorise. So we go to our quadratic formula, and prior to yesterday, we would have said, oh, hang on a sec, square root of negative 19, no real solutions. But now, of course, we know that that surd can be simplified because we can rewrite it as the square root of minus 1 times the square root of 19. And so we get the square root of 19i, and we get two solutions. Of course, every quadratic now can be solved by completing the square. So x squared plus 3x plus 7 equals 0. Half the coefficient of x is 3 on 2. Now when I square 3 on 2, I get 9 on 4. But I want 7. And 7 is 19 on 4 more. Now before this was a problem because I got plus 19 on 4. But now that we can play with I, we can change that to the difference of two squares. So instead of looking at it and thinking of it as plus 19 on 4, we can look at it and think of it as minus 19 on 4i squared. So everything will end up being the difference of two squares. And so then I can just say, oh well, x plus 3 plus the square root of 19 on 2i, x plus 3 on 2 minus the square root of 19 on 2i. So I guess it just gives us an alternative way of solving quadratics. Rather than going to the formula, we could complete the square, creating quadratics. If quadratics have real coefficients, and that's the important part, then the solutions will always be in conjugate pairs. Because if you think about it, you would substitute into the quadratic formula and you end up with plus or minus the square root, and that's the bit that's going to become imaginary. So you get plus or minus the imaginary part, conjugates. So that'll be true as long as the coefficients are real. So watch out for that, because sometimes they've given questions where they say something like, oh well, 1 plus I is a solution to this quadratic, but one of the coefficients might be imaginary. And so people go, oh, 1 plus I, therefore 1 minus I is a solution. Not true, if the coefficients are not real. So they've got to be real for this to be true. If it is true, then I know it can factorise x minus z, x minus its conjugate, and if I was to expand that out, you see what we get. We get x squared minus z plus the conjugate of z. Well, if I'm adding conjugates together, the imaginary parts are going to cancel out, and I'll be left with twice the real part. And then at the end I get that z conjugate, which we've seen is the imaginary part squared plus the real part squared. So we'll always end up with something like that if we have to create a quadratic. So if I want one where it's 4 plus I, 4 minus I, writing this equation now is very quick. Because I can say, well, that's x squared minus twice the real part. Well, twice 4 is 8. So I know it's going to be minus 8x, or whatever pronumeral I use, plus the z conjugate, which is going to be the real part squared, plus the imaginary part squared. So in this case, 16 plus 1, 17. So yeah, you wouldn't write this down. This is what we're saying in our head. So sum of the roots would be 8, product of the roots would be 17, so we end up with x squared minus 8x plus 17 equals 0. Finding square roots, not just of real numbers, but now finding square roots of imaginary numbers as well. So a plus ib is going to be the square root of x plus iy. Well, one of the ways we do it is we square both sides. And then on the left-hand side, when I expand out, I get a squared plus 2abi minus b squared, and we equate real and imaginary parts. Okay. So, there we go. We don't need to do this working out every single time. We just remember that, well, a squared minus b squared is going to give me the real part, and 2ab will give me the imaginary part. So if I have to find the square root of negative 12 plus 16i, well, a squared minus b squared will be the real part, negative 12. 2ab will be the imaginary part, 16. Simultaneous equations. So b will be 8 on a. Sub that back in on the first one. So I've got a squared minus 64 on a squared is negative 12. Turns into a quadratic. Well, it's a quartic we can treat like a quadratic. A squared minus 4, a squared plus 16. Two possibilities. Either a squared equals 4 or a squared is negative 16. But actually, there's only one possibility. Because in this case, a squared can't equal negative 16. Because a and b are real numbers. Yes, b is the imaginary part, but the answer to that is a real number. And so I get a is plus or minus 2. Going back over here then, b must be 8 divided by the plus or minus 2. So we'll get plus or minus 4. Actually a bad way of writing the answer, because that kind of implies 4 solutions. So there's my square root. Plus or minus 2 plus 4i. Now this is where some people will disagree. Some people will say, oh no, it's just 2 plus 4i. Because you're asking for the positive square root. Same as if I said, what's the square root of 4? You would say 2, not plus or minus 2. Problem with imaginary numbers is, that's fine, it kind of is obvious when you have 2 plus 4i. Imagine that answer was 2 minus 4i. So, is it 2 minus 4i, or would it be minus 2 plus 4i? Which is the positive answer? Well, neither. You can't order imaginary numbers. So I maintain you put both down. Some people actually define it, and I think in one of the textbooks we've got there, they actually define it to be the square root, the positive square root is where the real part is positive. And so they give their answers that way. I always put plus or minus down. So a plus ib, square root of x plus iy. Here's an alternative way of doing it, which is kind of neat. We just saw that. A squared minus b squared is x, 2ab is always equal to y. Now, I could rewrite this, so just through algebra, I could go, well, x squared plus y squared turns out to be a to the power of 4 plus 2a squared b squared plus b to the power of 4. So, using that, if I've got this question, square root of x plus iy is a plus ib, I can say, well, a squared minus b squared is x, and a squared plus b squared is the square root, again, that real part squared plus imaginary part squared. That is an easier simultaneous equation to solve. Because you just add them and the b squareds cancel, subtract them, the a squareds cancel. So it tends to be really quick. Now, how do you know whether the signs are the same or different? Well, it turns out if the imaginary part is positive, then a and b will have the same sign. And if the imaginary part is negative, a and b will have a different sign. So back to our question, square root of negative 12 plus 16i, I could now go, well, a squared minus b squared, that's the real part, same as we did before. But now I'm going to say a squared plus b squared is the real part, the square root of the real part squared plus the imaginary part squared. 12 squared, 144, 16 squared, 256, add them together to get 400. Square root of 400 is 20. So 2a squared is 8, a is 2, and subbing back in b is 4. You get it reasonably quick. Now, in this case, the imaginary part is positive, so I know the signs will be the same. So therefore, it's plus or minus 2 plus 4i. Okay. Now, this works beautifully if the numbers are nice. Have a look at this one. Looks fairly simple, square root of 5 minus 4i. Where could the damage be with this? Well, a squared minus b squared is 5. Easy enough. Oh, a squared plus b squared, the square root of the real part squared is 25, the imaginary part squared is 16, add them together 41, we don't have a nice neat square root of 41. Oh well, we'll persevere. So 2a squared is 5 plus the square root of 41. A squared is half of 5 plus the square root of 41. So a is the square root of 5 plus root 41 over root 2. In this case, I'm going to rationalise the denominator. There's just too many square root signs there. So I get a half of root 10 plus 2 root 41. Well, that's a. So b squared, well, I can rearrange this one. B squared will be a squared minus 5, and there's b. The imaginary part there is negative, so they will be different in sign. So there you go. The square root of 5 minus 4a is plus or minus a half outside of root 10 plus 2 root 41 minus I root negative 10 plus 2 root 41. So why the other one was nice and this one wasn't? Have a look at the numbers. Here I've got 5 and 4. The last one, my numbers were 12 and 16. Why is 12 and 16 nice? Pythagoras, but what's the word? It's a triad, yeah. So if it works out to be a Pythagorean triad, then it's nice. Let's solve this equation. So it's a quadratic. Well, I'm going to use the quadratic formula. It's just that I'm dealing with imaginary numbers. I end up with the square root of minus 5 plus 12i. So, all right, I've got to work out the square root of minus 5 plus 12i. 5, 12, 13. Pythagorean triad. The other method will work nicely. So, a squared plus b squared, a squared minus b squared will be the real part, negative 5. A squared plus b squared will be 13, that hypotenuse of the Pythagorean triad. 2a squared is 8. A is 2. Imaginary part is positive, so the sign will be the same. And so b is 3. So over here, the square root is plus or minus 2 plus 3i. And tidying that up, I get my two solutions, I and minus 2, minus 2i. That shan't do us.